test response compaction. So, it comes into the overall diagram can be shown like this, that the test patterns that are coming from the ATE. So, that is after so there may be a decompressor here. So, that is not shown explicitly. So, after that decompressing, the test patterns are applied to the circuit under test. Now, circuit generates m bit wide output pattern. Now, out of that m bit, so the space compactor will generate a p bit wide output response. So, output pattern. So, it a typical case can be that it just selects p of the outputs out of m, and then it is coming as this p bit pattern. So, that is one possibility, but naturally if we just select p out of m bits, then p out of m outputs, then naturally many of the outputs are not contributing in the signature part. So, normally we put some network there, the space compactor is a network which will be combining the responses, and accordingly this and it is an m to p circuit. So, m input p output circuit. So, what network we put inside, so that will decide the quality of the space compactor. On the other hand, for time compaction, so test patterns are being applied to the circuit under test. So, so there are n also if there are n input patterns, so there will be n output patterns. So, out of this n output patterns, so we do not want to remember all the outputs, but maybe we remember q such sequences. Now, q output pattern, so in the ideal case, the q is equal to 1, where we remember only the final value that we have got. Naturally, what we want is we want to have the impact of every response loaded, so have impact of every response available in the final signature that we have. So, that way this time compactor is going to be useful in reducing the responses in the time domain. So, again there will be some summation that will be done, some signature computation that will be done. So, some network will be put there, so that it does a compaction in time. So, both this space compactor and time compactor, so they are going to be used in such a fashion that we can store only maybe 1 or 2 signatures from the for the entire test session. Now, there are many schemes that can be has been reported. Some of them are linear, some of them are non-linear, some of them do space compaction and time compaction both, some of them do only space compaction. So, we will look into some of these strategies. Now, space compaction. So, first one is zero aliasing linear compaction. So, we want that due to this compaction, these responses are not mixed up. So, it means that the one faulty response that should lead to a faulty signature. So, it should not get same as the correct response. On the other hand, if I have got say 2 faulty responses, then it is expected that those 2 faulty responses, they should give rise to 2 different signatures. So, that in that case I will have a zero aliasing linear compaction. Then there are certain other strategies like XCompact, XBlocking, masking, XImpact, etc., that are used for this compaction process. So, zero aliasing space compaction, linear compaction, it says there are 2 results. It says that for any test T for a circuit that implements function C, there exists a zero aliasing output space compactor C with Q outputs, where Q is given by log 2 T plus 1. So, this is a result. So, for any circuit, so I can have if it has got if I have got T as the test set size, then this mod of T is actually the size of the test set. So, we can always have we can always come up with a circuit C that has got Q outputs, and this Q is equal to this, and there will be zero aliasing. And if another result says that if G be a response graph, so what is a response graph we will see, and if G is 2 to 2 power Q colorable, then there exists a Q output zero aliasing space compactor for the circuit. So, what is a response graph that we will see. So, suppose this is this is the test set that we have, and this is the circuit that we have, and these are the patterns that are applied 0 1 1 1, and if we apply the first pattern, then the response that we get is 0. Then if we apply the next pattern, we get the response as 1. So, like that it is different responses are obtained in y1 line and y2 line. So, when the fault f1 is present, then this response changes from 0 0 to say 1 1 or 0 0 to say 0 1. So, what happens is that when a particular fault is present, then from the fault free response, the response changes to some other pattern. So, this is actually the response graph that we are talking about. So, under the presence of a particular fault, if the response changes from the fault free response to something else, then we have an edge between the two. So, that means under the presence of some fault, response changes from 0 0 to 0 1, but there is no fault in the circuit that can change this response 0 1 to 1 0. So, that is not possible. However, if 0 0 is the good response, so we see that due to the presence of different faults, so it can give rise to different response, different other responses, and we add edges in those cases. So, this is actually the response graph, and this result says that if the graph G is 2 power q colorable, then there exists a q output zero aliasing space compactor. So, coloring of a graph means if I have a graph, then I want to put I want to give some color to the nodes such that if two nodes are having same having an edge connecting them, they should not have the same color. So, if you want to color this graph, then suppose this node I color as red, then these none of these 3 nodes can be colored as red. So, maybe I color it with a green. Okay. So, then since this red and green are already used, so I cannot use those colors for this one. So, I have to use a third color here. So, this is say blue. Now, you see that this node for this node I do not need a new color. So, because this green color can be used to color this one also. So, you see that 3 colors are sufficient for coloring this particular graph. So, that is the result. It says that if it is 2 power q colorable, so naturally the graph is 4 colorable, so taking it a power of 2. So, there will exist a 4 output zero aliasing space compactor for this circuit. So, since this graph is 4 colorable, so we can have a compactor that will have 4 outputs. Now, in this particular case, of course, it is not very important, because this original circuit has 2 outputs. So, now I am telling that I will have a compactor that will have 4 outputs. So, it is not acceptable, but in general you can say that if the number of outputs are large, then we can construct this graph, and taking help of that theorem. So, we can come to a network which will be which will give us the space compaction without aliasing. So, next we will look into this space compaction techniques. First one in that category is the XCompact. So, this is X tolerant response compaction technique. So, what happens is that it will tolerate the X's, the unknowns that can come in the response. So, it will tolerate that. So, it will have a matrix which is called XCompact matrix, and then this error masking will be utilized. Now, this XCompact, so it has the basic idea is like this. So, it will frame one XOR network. Okay. So, in this XOR network, this scan chains, so it has got say 8 inputs. So, this scan chain, these 8 inputs are coming, and then this 5 outputs are there, 8 input 5 output. Now, this network is constructed in some fashion. So, these scan chain values are added using these XOR gates. Okay. But how this compactor is fabricated, so that is actually given by these 2 theorems. So, it says that if only a single chain produces an error at any scan out cycle, the XCompactor is guaranteed to produce errors at the XCompactor outputs at that scan out cycle, if and only if no row of XCompact matrix contains all zeros. So, it says that, so XCompact matrix is this one. So, this is the XCompact matrix that gives the connection that we have here. So, this connection, say this output 1, it is basically a sum of this scan chain 1, then this this is basically a sum of this scan chain M transpose into S. So, M transpose if we take, so it is basically the sum of all these scan chains. So, SC1, SC2, SC3, SC4, SC5, SC6. So, if you look into this diagram, you see that here I am taking SC1. So, here I am getting SC3, here I am getting SC4. So, these three are coming to the first XOR gate, and for the second XOR gate I am getting SC2, then this one, that is SC5, and this one, that is SC6, and then at the output of this XOR gate. So, all these up to S6 SC6, all these XOR all these scan chain values are going to be added to produce this output 1. So, this matrix also, if you take M transpose into S, so what you are getting is that this particular column, so 1 1 1, so they will get multiplied by this S, and that will be defining the O1. So, that is the structure of the XCompact matrix. Now, it says that if the XCompact matrix has got this property, that is if it has got no row of XCompact matrix contains all zeros. So, if this condition is ensured, that in that case any error that is produced in some scan out cycle. So, if the error comes only in a single scan chain, if only a single chain produces an error at any scan out cycle, then this XCompact matrix will be able to catch that error at that scan out cycle. So, the compacted output also will have a different value at that particular scan out cycle. So, it is true if only a single chain produces an error at any scan cycle. Now, if there are multiple chains that produce error, so errors from any 1, 2 or an odd number of scan chains at the same scan out cycle are guaranteed to produce errors at the XCompactor outputs at that scan out cycle if every row of the XCompact matrix is non-zero, distinct and contains odd number of ones. So, this is another constraint that is put on the construction of the XCompact matrix, that the rows they should be non-zero, the rows should be distinct, and each of them should contain an odd number of ones. So, if we look into this XCompact matrix that has been used here, so this contains odd number of ones, all of them are containing odd number of ones. So, and none of them are 0, all of them are distinct. So, none of them are same. Okay. So, all the three properties are satisfied. In that case, so it says that with this particular property will be satisfied, that is error from any 1, 2 or odd number of scan chains at any scan out cycle will produce some erroneous output at the XCompactor outputs. Okay. So, actually, so if any of the say odd number of chains are giving faulty result like SC1, SC3 and say SC6, they are giving faulty result, then out of this out1, out2, out3, out4, out5, so at least one of them will produce the output which is different from the fault free output. So, that way it ensures that whatever is if there is some fault occurring and it is coming to the scan chain. So, the circuit is producing a different output and it is coming to the scan chain. So, the corresponding test pattern could detect that particular fault, then this compactor circuit is not going to lose that particular detection. So, it will pass that detection to one of the outputs, and that way it is guaranteed that this the aliasing will not occur, the faulty response will not match with the fault free response for that particular cycle. So, this is the beauty of this XCompact scheme. So, we can construct this network. Of course, there are catches, like say if there are even number of chains fault, then this none of these results tell anything. Okay. So, if there are even number of faults, then of course, we cannot do anything. So, but it is very much likely that this even number of faults, so it is, if some test pattern create even number of errors, then of course, there may be some other test pattern which will detect it at an odd number of scan chains, odd number of outputs for the circuit under test. As a result, it will produce faulty output at odd number of scan chains. So, as a result, it will get detected by the second pattern. So, that way so this is a very good approach for doing the space compaction, where we can without any aliasing occurring. Another possibility is space compaction is known as XBlocking or XBounding. So, X's can be blocked before reaching the response compactor. So, we can say that if there is some unknown value coming, so we can block that value. So, it can we can ensure that the X's no X's will be observed. So, it is unknown. So, we can stop it before it reaches the compactor. So, basically the idea is like this. So, if we know that a particular scan chain can produce some unknown value at a particular point, so we pass it through a multiplexer, and this multiplexer the other input is 0. So, if we know that at this particular test pattern the output of this scan chain is going to be undefined, then we can put this select line, so that it passes a 0 to the compactor. So, the effect of this particular scan chain will not affect the compactor operation. So, that is one X blocking operation in the space compaction. Another possibility is X masking. So, the X's can be masked off right before the response compactor. So, they can also be masked off. So, masking, I think, so this is the thing. So, we have got a mask controller. So, again the same thing. So, this scan out the scan chain outputs are coming. So, we know that this particular line has to be masked out. So, we can put the mask controller can put a 1 here, so that this one gets masked off. So, this mask controller it continually generates masks. Okay. So, as this scan shifting operation is going on, so this will continually generate masks, so that whichever pattern, whichever mask, whichever scan chain has to be allowed, so that will go, and in that case this mask bit is 0. On the other hand, if the mask bit is 1, then the scan out bit will not go. So, it will get a 1 at the compactor input. So, this way we can have this X masking circuitry, so that this these unknown values do not reach the space compactor. Next, we look into the time compaction. So, space compaction, what it has done? It has ensured that out of say m outputs from the circuit, or the m scan chains that we have, so it has selected, it has combined those m outputs in some fashion, so that it gives say p outputs. But for each test pattern, so it is for each scan cycle, so it is giving us one such p bit pattern. Okay. So, because this continually these scan out operations are going on, when the next pattern is being shifted in, the previous response is being shifted out. So, over the entire scan operation, this p bit responses will continue to come. But if we store all those p bit responses, then again there will be huge amount of information that needs to be stored. So, what is done is we compact these responses in the time domain as well. So, this is known as the time compaction. So, time compactor, it normally uses a sequential logic to compact test responses. So, time compactor we cannot do with combinational logic, because combinational logic does not have any memory. So, that way, so it will lose its content at the previous cycle, whatever had happened in the previous cycle. So, this combinational logic cannot be used. So, we go for a sequential logic to compact the test responses. The most widely used structure is the MISR. So, this MISR, so this can continually receive the responses, and they can be combined into one value. So, this actually we know that if MISR has got a polynomial its structure is represented by a polynomial, and the inputs are being fed. So, whatever remains in the MISR after running for some number of cycles is basically a division operation, that is the remainder of that input stream getting divided by the polynomial. So, that will come as the signature. So, and any n stage MISR can be described by specifying a characteristic polynomial of degree n. So, this we have already seen in the BIST chapter. So, if this is one multiple input signature register, so we have got this R 0 R1 up to R n minus 1. So, this is represented by this characteristic polynomial 1 plus h 1 x plus h 2 x square h n minus 1 x n minus 1 plus x to the power n. So, depending upon the values of these h's, so this characteristic polynomial is getting defined. Now, these responses that are coming from the scan chain, so they are connected to these lines, these m lines m 0, m 1, m 2, m n minus 2 up to m n minus 1, or say this is a typical example where we have got this a typical one particular connection, and this M0 M1 lines, they are connected like this. Now, you see, so if you trace through this operation, like in the first cycle, so initially all these contents are 0. Now, this M0 is 1. So, this cell will get a 1 after some in the after the first cycle. Then after the second cycle, the M0 is 0, and it will depend on what value it comes at this point. So, it is basically at this point this is 0. So, 0 is coming here. So, this will again get a 0. So, this way this division will take place. So, ultimately it will produce this particular pattern 1 0 0 1 1 0 1 1. So, that is the pattern that will be that is the actual the representation. So, the same message bit that we have over number of cycles can be represented by a single message bit like this. So, what the remainder will be coming is nothing but division of this message bit by this fx, by the characteristic polynomial fx. So, we can also have mixed time and space compaction mechanism. So, you see what has happened is that this circuit, so this is coming from the scan chain side. So, it has got 1 2 3 4 5 6, there are 6 inputs, there are 6 scan chains that are coming, and I have got, so this XOR network. So, this is forming the it is some sort of space cum time compactor. So, see, instead of feeding a single value, what we have done, we have fed here 4 values. So, here I have fed these 3 values. So, here I have fed these 4 values. So, this is basically the space compaction part, plus this flip flop connection is going there. So, this is also XOR. So, this is basically the time compaction part. Ideally, we should do first the space compaction. So, this is basically the circuit. So, here I have got this response. So, these are the responses coming. So, this is passing through the space compactor, and then it produces some less number of inputs, less number of output, that passes through a time compactor, and so at the end of this time compactor. So, this will have the golden response stored here. So, golden signature at the end, this time compactor will have the golden signature in it. So, the circuit that is shown in this particular diagram, so here it is done combinedly. So, this space compactor is nothing but some XOR network, and this time compactor is nothing but some MISR. So, this XOR part can be merged together, and we can come up with a structure like this, which combines the space and time compaction jobs together. Okay. So, that way it is a mixed time and space compactor. There are several standards industries like OPMISR, then embedded deterministic scan, virtual scan, adaptive scan, etc. Now, these linear decompression based schemes. So, there are some schemes which are based on linear decompression. So, these are the schemes like ET compression, logic vision, test compress, mentor graphics tool, then SOC beast, synopsis tool. So, they are based on linear decompression. And broadcast scan based schemes. So, we have got SPMISR plus, then the tool from Cadence, virtual scan, ultra scan, DFT max from synopsis. So, they have got this type of solution, broadcast scan based solutions. So, we look into this OPMISR plus structure. So, here what happens is that we have got this scan chain. So, they are going into this broadcast scan mode. In the broadcast scan mode, so these scan chains are loaded. Now, there is a mask. So, this scan, whenever the patterns are getting loaded, then this mask control is also loaded. So, as a result, when these responses are coming from these scan chains, so depending upon the mask bit, some of the responses will be allowed to come to this MISR, and others will not be there. So, that way it is it will be doing this, it will be coming to this MISR. As a result, it will do a space compaction, and this finally we get this result. So, here here the time compression is done first, and then followed by the space compression by this space compactor XOR network. So, that way it is a composite MISR observed. So, that is the output part. So, there are many other standards. So, you can just go through some literature on that. In to conclusion, so like test compression is an effective method for reducing test data volume and test application time with relatively small cost, because it reduces the cost, because because we don't need to use more advanced ATE to store huge amount of test data or apply the test at a higher frequency. At a low frequency also we can just transfer the pattern set, and then we can using a decompressor we can just decompress the test patterns and apply to the circuit. And then we can also do some response compaction. By response compaction we can combine the responses into one or two signatures, and that way this amount of information to be stored for response will also be less. So, we can do this operation. So, we can do the comparison part easily. Now, it is easy to implement and capable of producing high quality tests. So, we have seen that there is zero aliasing space compactors are available. Then for this time compaction also these LFSRs they show very high aliasing rate. So, as a result we can say that the faults will not get aliased, the responses are not getting aliased. So, that way we can have a very good scheme when this test compression is put into operation. Of course, we need to unify different compression architectures. So, there are different architectures, we have seen only OPMIS plus, there are other architectures as well, but as a result what has happened is that standardization is a question. So, which one can be a standard architecture, so that has to be decided.